Here are the notes for section 6.2. We'll be talking about properties of light. So here I've got a photograph of a pinhole camera. A pinhole camera is simply a cardboard box. And then in the cardboard box, I've blocked all of the little holes. And then I have a piece of tin foil. And what I did was I used a pin to punch tiny holes in the tin foil there. They're kind of hard to see. Then I turned this lamp on, this lamp here, and I looked at it from inside the box. I kind of stuck my head inside the box. So here's a picture of the light aimed at the box, and then I would be over here looking, and I put a translucent screen between me and the box. I actually used, for the translucent screen, I used this Rubbermaid Tupperware lid thing. So that's what I had going on. And this is a ancient type of photography, really, called a pinhole camera or a camera obscura. And it actually creates images. So if you just look inside the box, you'll see the 3 holes with light coming through. And if you put the screen up, you'll actually see an upside down image of the lamp. Now these are a little bit blurry, but you can kind of make out the bulb, and you certainly can see the arrow. And again, that is the arrow that is on this bulb here. So we will be trying that out in class. But the pinhole camera is really instructive because it shows us some of the properties of light. We think of light as behaving like a ray, just like a ray in geometry. It has an origin. In this case, light is being emitted from the light bulb, and then it travels in straight lines like this. What we like to do is we think about 1 or 2 representative points on the object. I usually pick the top and the bottom as my representative points. Then the light coming from that object, whether it's being emitted, like from a light bulb, or whether it's being reflected, like from just an ordinary object that's reflecting light, that's what we see. We see these light rays that are either being emitted or reflected. What the pinhole camera does is it geometrically selects a tiny amount of that light. So here I've got 2 rays that happen to fit through this opening. And what happens is they maintain the order of the original object. So the bottom of the object flips to the top and the top flips to the bottom. When you move the screen back, what happens is you have the same amount of light, so the image gets a little dimmer and a little grainier. It's the same amount of light and information, but it's spread out over a greater area. And if we were to change the relative position of the screen and the camera, we can see what would happen. If we've got a screen that's relatively close and an object that's relatively far away, we get a very small image. If we increase the size of the pinhole, we see brighter but out of focus reproductions. And if I go back, that's what's happening here. You can see as I go up. So this is from the smallest pinhole, and this is the largest. The image produced from the largest pinhole. And you can see it's more out of focus and blurrier as we increase the size of the pinhole. Okay. Also, if I have more than 1 pinhole, I get more than 1 image. So again, we're not going to study pinhole cameras per se, but I do think it's helpful to think about some of this language. We've got an object, we've got an image, and we've got something in between. In this case, a pinhole. We're going to look at situations with lenses, with mirrors. But first, we're going to look at situations with just a transparent or translucent material to see how that affects light. So in the last section, we talked about how light slows down due to a medium. So actually, I'm going to come down here to this index of refraction, and I apologize for this font. Didn't work out quite the way I'd hope. But just a reminder that the index of refraction is equal to the speed of light in a vacuum divided by the speed of light in a medium. So light does slow down in a medium. Oops. And that slowing down of light has consequences. It makes the light bend. So I'm going to use an analogy from my childhood, and I don't know if this will work for you all or not, but we'll give it a whirl here. Let's say that I had kind of like a go-kart, some little car with 4 little wheels, and I'm going to cruise on my go-kart on the concrete. Okay, so I'm cruising along, and then, let me take a picture of this. And then I'm going to get to the grass. Now, what is going to happen when I get to the grass? So I'm on the concrete, and I'm going to go faster. On the grass, I'm going to go slower. So the speed reduces. Now, if I'm traveling at an angle, what happens is this wheel slows the first before this wheel. And what happens is that actually allows this wheel to catch up a little bit. So it might actually make up some ground. And what happens is the path of the object, oops, try that again. The path of the object is going to straighten out a little bit. Now, the way that we would say that in terms of physics is we would say that the direction of the cart moves toward the normal. So what I just drew here was the normal to the boundary. This line here is called the boundary between the concrete and the grass, pardon me. And our initial angle is bigger than our final angle. And indeed, this is what we see happens. The exact same thing happens with light traveling through a transparent medium. So let's say that I had light traveling through air, and let's say that light hits at an angle. First of all, we can measure that angle. We always measure it from the normal, and we call this the angle of incidence. The word incidence in this case kind of means it's the same thing as the first angle, okay? Then what's going to happen is the light is going to bend. Not that much, though. That needs to be a straight ray. The light will bend toward the normal line. So when the light slows, it bends toward the normal. And this angle is the angle of refraction. Okay, refraction means bending, literally. Now, it's also true that if the light were to go the other way, so if I were to send a beam of light going this way, in the opposite direction, it would bend away from the normal when it speeds up. And it would follow exactly the same path if this initial angle was the same as the old refracted angle. The other thing we need to know is that light takes the shortest possible path given the indices of refraction. This is the shortest possible path all the way through given the n values and speeds. So the idea here is that when the light slows, it's going to go a distance that's a little bit shorter than if it had not slowed down. So the light ends up taking the shortest possible path, or the path of the least amount of time. Okay, so if we look at these, if we look at this, and let's go back to our original, if we look at these two angles, Snell's law gives us the relationship between those values. Snell's law says that if we've got two media, and we'll call this the incident and this the refracted, and I'll just sketch it here so we can look at it while we're working on this. There's my incident angle. There's my refracted angle. Snellius was the name of the man that took credit for this. I learned that he was not the person that discovered it, but we can talk about that in class more. He was a Dutch guy, Snellius, and they shortened it to Snell. Anyway, this is Snell's law. Now, I'd like you to take a moment and think about what would happen if, a couple things about that, actually, before we go on. The sign, think about what the sign is here. Okay, we were working with the normal, right? And if I were looking at this, if I were looking at this as a right triangle, the sign would be related to the opposite side, right? So you kind of have this sense of the sign being a measure of how far this thing has bent. Okay? Okay, now let's think about this for a second. What if I were to measure these signs for a certain substance and graph it for different angles? We're going to do this in class. One thing that I want to, or maybe we've already done this in class, but regardless, I want to make sure that I'm clear about this next part because I saw lots of questions on the AP stuff. Oh, let me switch this around. Let's do this. Okay. If I graphed the sign of the refracted angle against the sign of the incident angle, what would I wind up with? Let's think about that for a second. So if I take this and think about it in terms of y equals mx, can you figure out what m would equal? I would need to divide both sides by n sub I. So the sine of, oh, this is r, sorry, I'm going backwards. So actually, I would need to divide both sides by n sub r. So I would say the sine of the refracted angle would equal ni over nr times the sine of the incident angle. And my thinking here is that on the horizontal axis, I've got the sine of incident. On the vertical axis, I've got the sine of the refracted angle. And look what happens here. My slope is the ratio of these indices of refraction. So the slope in this scenario is equal to ni over nr. Pretty cool, huh? If ni happened to be air, which is about 1, then the slope would be 1 over the index of refraction of the material that I'm studying. And again, that's what our lab is all about. Okay, so, and let's answer these two questions. In what cases will light be refracted toward the normal and away from the normal? So if I go back up here, we saw that it goes toward the normal when the light slows down, and it goes away from the normal when it speeds up. Okay, so let's do some examples. A light ray strikes an air-water surface at an angle of 46 degrees with respect to the normal. Okay, I'm going to make a little sketch of this. So I'm going to have air, water. I'm going to draw the normal. I'm going to draw the light ray. Okay, 46 degrees is going to be my incident. Given that the N of water is 1.33, find the refraction angles when the direction of the ray is from air to water and then from water to air. Okay, so we'll do air to water first. So water has a higher index of refraction than air, so I'd be looking for this refracted angle. So Snell's law tells me that Ni sine theta I equals Nr sine theta R. So I would do 1 times the sine of 46 equals 1.33 times the sine of unknown. And now I need a calculator. I'm going to make sure that I'm in degrees. And I end up having to take the inverse sine of the sine of 46 over 1.33. And I get 32.7 degrees. There we have it. And then we're supposed to do it the other way. So here's what that means. So, oops. There we go. So now what if these two things are reversed? What if we have water here and air here? So we would say 1.33 times the sine of 46 equals 1 times the sine of the refracted ray. And here, this number is 0.95. Now, what we're going to see in a little bit is if this number goes over 1, you can't do that. You can't take the inverse sine of a number greater than 1. So there are situations where the ray is reflected and not refracted. We'll look at that in a moment. But for now, I'll solve this one, and I get 73 degrees. So as it speeds up, it's bending away from the normal. Okay, in these next pictures, let's see. So if this are water, let's just kind of test our thinking here. If it's water and it slows down, it's going to bend toward the normal. Okay, and let's say this were glass with an N of 1.52, that's what window glass is. It would bend, oh no. Oh, that is really a bummer. Okay, well, it would bend toward the normal even more if we were going from water to glass. What's crazy is it will come out, we could do the math on this, but it will come out at the same angle that it went in. It will bend back so that these are parallel. Okay, let's hit a couple more highlights here. The index of refraction changes for different wavelengths of light. So there is kind of a neat simulation of this. So here it is, dispersion of light. So this is a prism, and what this is showing is that the purple light bends more than the red light. So up here, I can actually set the index of refraction for the outer portion and the inner portion. The inside here, we're saying this is 1.58. That's probably like glass. And then you can see the percent difference between the red light and the purple light. So this is what this property, this fact that the index of refraction is different for different wavelengths, different frequencies, is what allows rainbows to happen. Uh-oh. So, I saved some of it. So looking at this question, a beam of white light is an incident on a triangular glass prism with an index of refraction of 1.5 for visible light. Initially, the prism is in a glass aquarium filled with air. If the aquarium is filled with water, what happens? So basically, what they're saying is we're beginning with an index of refraction of 1.5, and out here it's 1. But then what would happen if we changed this and made it 1.33? And the answer is the closer these n values are to each other, the less bending we have. One example of that, and I think I showed this to you previously. Let's see if I can find it reasonably quickly. There it is. One example of this is this. This is vegetable oil in a Pyrex beaker with test tubes inside of it. And there's actually 2 test tubes here. They're hard to see. Oops. They're hard to see. There's 2 test tubes here. One's on the left, one's on the right. And the reason you can't see it is because the indices of refraction are almost the same. So what's going to happen is we're going to have less separation between red and violet when we bring the indices of refraction closer together. Okay, final big idea for today, total internal reflection. What happens when we get to a certain critical angle is that we don't have bending of light. We actually have no refraction at all. The light stays inside. The boundary between refraction and reflection is having a refracted angle of 90 degrees. So if we take Snell's Law, and let's say that this is, this is N1 and this is N2, like it's written. If we say N1 times the sine of the critical angle equals N2 times the sine of 90, okay, so we're saying that's 90. We can solve for the critical angle. The sine of the critical angle is equal to N2 over N1 because the sine of 90 is just 1. And that's what we have written down here. So let's try this. If the angle of incidence is 45 degrees and the angle of refraction is 33 degrees, first sketch the situation and then find the index of refraction for the substance. Okay, so what I'm going to assume here, this is 45. This is 33. I'm going to assume this is air. And this is the index of refraction that I don't know. So I'm going to say, 1 times the sine of 45 equals n times the sine of 33. So n equals sine 45 over sine 33. Okay, this is kind of review of what we've been doing. And I get 1.29. Then it says find the critical angle for the substance. So what we're asking here is Now if I were to turn the light beam around, what is that critical angle that produces a refracted angle of 90 degrees? So I'm going to say 1.29 times the sine of the critical angle equals 1 times the sine of 90. So the critical angle is going to be the inverse sine of 1 over 1.29. And I get 50.37. And if I go past that with my beam of light, what happens is the light stays inside of the substance. All right.